Hi everyone, I think we can start. So today, today I'll be discussing mostly about the parameter estimation. So we discussed about the probabilities and the probability distributions yesterday. Does anyone have any questions on that before I move on to this topic? Okay, it seems not. So I can discuss now about the parameter estimation. Let's see. Again, the books that I have is mostly the same. So let's see what we want to do. Before I go to that, so let me introduce a few more definitions that is needed. So let's say we have some random variable x, and which is described by some PDF f of x. Okay. Now we can define something called sample space. I also discussed yesterday a little bit about sample space. So basically, the set of is a set which contains all possible values of x, which we call it sample space. Now a sample, or you can say data sample or something, it's basically a set of n independent observations. So when you perform some experiments, some repeatable experiments, so you have some independent observations of x of the variable that is of your interest, and this is the set of all these observations. We call it a sample of size say n. Okay. Now you assume that all these observations are independent, so they are basically the all xi are independent. So you can write the PDF or the joint PDF for observing all these events. Okay, in n times is basically the f of, you can write f of x1 to xn, which is the product of the probabilities to get that particular observation, right? Given f of x, which is the PDF, the getting that particular event is it's the f of xi, and then getting all these n different observations. So it's a product of these probabilities, right? Now, imagine that we have, say, n measurements of x, but the PDF is not known. Okay. So what we want to infer is that given n measurements, okay, we want to infer what is the PDF of those observations. Okay. Now, suppose we have a hypothesis that we think that the events come from this kind of this is the kind of events, or this is the from this theory we expect this kind of events or so on. So we have some hypothesis that describes these events, or the PDF of these events. Okay, PDF of these observations, and this PDF, okay, hypothesized PDF depends on some parameter theta, which is not known to us. Okay, some unknown parameters. Now you can have a small, simple example. For example, you can have, say, we have a radioactive source whose lifetime is not known, so it's an unknown source for us, and we know that the PDF of radioactive decay would be exponential distribution, depending on, and it depends on some decay parameter, right, or lifetime parameter tau. Okay, so the tau is unknown for us for this. Okay. Now the procedure to estimate this parameter, given that we have n observations or n measurements, which we call data, okay, is called the parameter. Okay, so that means that what we want to do is to construct a function of f of xi, or all functions of these observations, to estimate this parameter. Okay. Now let me introduce a few more definitions. So a function of these observed measurements x1 to xn, which contains no unknown parameters, is called a statistic. Okay, and a statistic which is used to estimate some property of a PDF. PDF means this is some hypothesized PDF, or that means property of PDF means we want to determine the corresponding value of the unknown parameter. Okay, it's called the estimator. Okay, so suppose we have a parameter theta, okay, of the PDF, then the estimator of theta is usually we write as theta hat, and the numerical value of that estimator, I mean, after you do the fitting, you get the numerical value for that estimator from a given data sample or given set of observations is called the estimate. Okay, so we'll be using this names later on. So if the estimator theta hat converges to the theta in the limit of large number of events or large n, okay, the estimator we call it to be consistent. That means, or we call it a consistent estimator. So that means in n tends to infinity limit, the probability that theta is equal to theta hat is equal to theta is when it happens, the estimator is called consistent. So this limit of large n is typically we refer as large sample or asymptotic limit. So when we talk about in asymptotic limit, this converges or this becomes consistent estimator or so on. So that means it basically refers that in a limit of large sample. Okay. Now let's see. We know that in the previous lecture we discussed that when we have a random variable, if we take a function of the random variable, then that function itself is also a random variable, right? Now here, this theta hat or the estimator is also a function of the random variable itself, and this is a function of the observations, right? From the observations we estimate that. That's why it is also a function of the observations or exercise. So in that case, theta hat is also a random variable with some PDF g of theta hat, giving the parameter theta, which is unknown. Okay. Now, the probability distribution of this theta hat is normally called the sampling distribution. Okay. Then that assume that you have a sampling distribution, then the expectation value of this theta hat that you can write, or the population mean, okay, that you can compute. Okay, I mean, you can write like this. So as integration of theta hat, g theta times d theta hat, right? Now you know from earlier yesterday also that if a is function of x, then integration of a f of a dA is same as integration of a f of x dx, right? So using that, we can rewrite this as again the integration over this joint PDF for having all these observations, given this PDF depends on the parameter theta times dx1 to dx. Okay, or this joint PDF we can expand it further, which is just product of individual PDFs. Okay, so if we know this, okay, or we have some hypothesis for it, okay, then the expectation value of theta would be computed by this way. Okay, so this is equivalent to, when this is basically the expected mean value of the theta from an infinite number of similar experiments. So when we say population means, this means population mean or expectation means that what is the mean that you get if you have infinite number of similar experiments giving some observations, or each having some sample size n. Okay. Now we introduce something called bias, okay, which determines the quality of your estimators. Okay, so the bias is basically defined as B equal to expectation value of this estimator theta, which depends on your observation x, minus the actual value of the parameter theta, okay, which is not known. Okay, now this B will of course depend on the sample size. If sample size is small, then you can have larger bias, for example, because of the statistical fluctuations. And also it depends on the functional form of the estimator and as well as the true properties of the assumed PDA f of x. It depends on theta. Okay. Now if this bias is 0, that means you do not have any bias, then irrespective of any sample size n, then theta hat usually is called unbiased. Okay. And in the other case, if b is tends to 0 in the large sample limit when n tends to infinity, in that case the theta hat is called asymptotically unbiased. Again, you can see that we use asymptotically when we talk about large sample. In most practical cases, the bias
Sir,
will
can I ask one question?
sure, yes.
Sir, so here we say the B is depending on the functional form of the estimator. So our theta cap is the estimator. So we choose. I mean, we already know some functional form of when we do the fitting, or I mean, because if it depends, then to start with, what functional form we choose for the estimator will be, I mean, very much dependent, and then there will be always some bias in the B.
The point that in some cases you can have the functional form of the estimator, but in some cases you may not.
Yeah,
Okay.
yeah, yeah.
So when you know the functional form of the estimator, suppose you will come to that. In some cases, you can actually know that some, for some kind of parameters, you can get a functional form of that. Okay. And
Mhm.
then in that case, of course, the bias depends on that. Okay. But sometimes you do not know the functional form, and you get this from Monte Carlo, from the feed directly and other things. So in that case, of course, the functional form may not be known.
Yeah, okay, okay, okay. Yeah, so I
Sir,
mean,
can I ask one question? That let us consider the x is a random variable and its PDF is fx, and our estimator theta hat its the PDF is g theta. So, does it necessarily mean that the structure of g theta and fx will be same?
No, 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 no. G theta is some PDF, which is the PDF of the estimator theta. Here, f is the PDF of the x, but theta hat it depends on the x. Okay, since this is a function of x, then we can write like yesterday we did for the function of x. When we say a is a function of x, then and if g a is the PDF of a, then we could write ga dA is equal to f of x dx, right?
Integration.
Yeah. So from that we can use this.
But
Okay.
GA may not be equal to the
Now,
fx.
ga doesn't equal to fx, but the changes, ga dA, okay,
Hmm.
it's could be
That will
written
be
as
same.
f of x dx. Okay.
Okay. And sir, if you have in the first slide, you have shown that we are showing if in the radioactive decay sample that we are choosing some samples which are following the same distribution function fx. Uh,
Which
so
one? Which you said this one?
no, in the previous slide.
Yeah, this slide you mean, right?
Yes,
Radioactive.
yes, yes,
Uh-huh.
yes. So let us consider one case where we are choosing some samples where a few sample are showing the different distribution function, uh, not equal
No,
to
no,
f
the distribution, the sample doesn't show distribution. I mean, sample is the observation, just the event that you observed, right? from some experiment.
samples PDF where you are writing that f of x1, x2 to xn equal to product of function
So
of
this is
xi.
if you know the x, right? If you know the f in that case, or you have the assumption that your hypothesis gives you the PDF. Is a hypothetical PDF, right? Suppose
Okay,
you
this.
know the f of x, then you can write the product of f. Now here in this case, suppose we got radioactive, from radioactive source, we got some observations. Since we know, I mean, we assume that radioactive, decay will be exponential. So that is our hypothesis, right?
Yes.
Yes. So that exponential distribution, the PDF, is our hypothesis that the radioactive decay will be exponential, right? With some parameter tau. So given that hypothesis, if we have set observation, we use some hypothesis to define what is the PDF, assumed PDF, right?
Yes.
Yeah, so that is what the f of x theta means here. Is the PDF which comes from the hypothesis. But the actual PDF of x may not be known to you.
Achha, achha.
You have some observations from experiment, and you are assuming that, okay, if my hypothesis is correct, and which depends on some parameter theta, then if I try to assume that these observations corresponds to this hypothesis, then what will be my parameter? Okay.
Okay.
Yeah. Okay. So now, yeah. So what I was telling is, yeah, in most practical cases, the bias would be small compared to the statistical error or the normal standard deviation. Okay. So most source of error uncertainty would be mostly statistical. That is in practical case. Now you can also write this statistical error, or standard deviation, which will come from this mean square error. You can define this as mean square error. Okay, I somehow matched up with my symbols. This E is same as this expectation. Okay. Yeah. So expectation of, you can write that as expectation of theta hat minus theta square. Theta is the exact value, right, for the theta hat, and which you can expand, and you can write that the mean squared error, total mean squared error, it's basically corresponds to the variance plus the bias square. Okay, and that means it is basically the variance corresponds to the statistical uncertainties. Okay, some of the squares of the statistical uncertainties, and the bias you can consider as a systematic answer or systematic error. Okay, now you can say an estimator is optimal if the bias is 0 and variance is minimum. Okay, or you can say an overall MS is minimum. Kind of. Now let's say we now define as, what there is one question about form of the functional form of the estimator. So we can now see a couple of a few estimators which, irrespective of their PDF, they have some kind of functional. So for example, if we say we take an estimator of the mean, okay, or population mean. Suppose we consider the sample of a random variable x with observations x1 to xn. Now the PDF f of x is not known, right? But without knowing the PDF, we can still estimate using the functional form of the estimator for the mean. Okay. Now you can construct the aim is to construct a function, okay, t, which is your statistic, to be an estimator for the population mean x, which is ideally the mean. Okay, that we call mean. Now we can take the arithmetic mean. So there was a question yesterday about what is the difference between the population mean and this one. So why we call that as population mean. So population mean is this expectation value, and then the arithmetic mean, which is simply the average over the observations, okay, or we call it the sample mean, where which we write that x bar is the average of x of I given n observations. So you can show that this sample mean is actually an estimator for the population mean. Okay. So there is one law called weak law of large numbers. Yesterday we discussed about central limit theorem. This is another similar law, which states that if the variance of x exists, then you can show that the sample mean x bar is a consistent estimator for the population mean in the limit n tends to infinity. Okay, that means in the large sample limit. So you can show that in the large sample limit, x bar converges to mean. Okay, so that's why we call it a consistent estimator. So there is similarly another law called strong law of large numbers. I'm not going into that. So you can note that this law actually holds irrespective of the form of the PDF. This simply doesn't depend on the PDF, okay? Except a few PDFs like Cosby, Landau, okay? You can tell me why it will not for this PDF it will not have this, this law will not be valid, okay? Do you know? Can you do you know if the variance exists for Cauchy and Landau? Anyone? Okay, you should find out. So in those cases, in these exceptional cases, you actually the x bar will follow the same PDF as the x. Okay.
Sir, why the existence of variance is a condition for this?
No, basically existence only when they have finite variance. This law is applicable to for those PDFs. Okay. So this PDFs doesn't have, like Cauchy, Landau doesn't have a finite variance. I mean, you cannot have a, of course.
Sir, because I mean this Landau distribution, I mean this distribution have a very long tail. That's why you don't have a finite variance. Is it
Exactly. Exactly.
okay?
So these two distributions doesn't have a finite variance, and this law is only applicable to those PDFs which has finite variance. But in practical cases, you can still get some variance from Landau and Cauchy because just from
But sir, you have to chop.
method.
You have to chop somewhere. Then in that case, I mean you will have some finite.
Yeah,
variance.
so that's what
Is it like that?
So from the functional form you cannot get, but if you just take the distributions and random observations from that PDF, then you calculate, from there you can calculate some number. Okay. Okay. Now let me go to next. Yeah. So here we can actually show that the expectation value of this sample mean, if you calculate this, you take the expectation value of x bar or the average, okay, then you can show that this will be equal to mu. Okay, so we saw earlier that if this is the case, then you can say that x bar is an unbiased estimator, right? So from this, this condition, we define the bias, okay, as mean of the estimator minus the actual value of the parameter, right? So if they are same, in that case b will be 0, and you can say this that sample mean x bar is an unbiased estimator for the population mean. So irrespective of the PDF, okay, you can actually use, if you want to just calculate the mean of given some observations, and you want to calculate the mean of the parameter, okay, mean is your parameter, then you can simply take the sample mean, and it will give you the it will be an unbiased estimator for the actual population. Okay. Similarly, you can have sample variance, which is defined as S square, which is defined as 1 over n minus 1. Okay, that you have to note. Okay. And sum over xi minus x average square. So if you expand it and do a little bit of algebra, you will find that you'll get it as n over n minus 1 x square average minus x average. Okay.
So why in the denominator it is n minus 1?
Yeah, this is the definition of this sample variance, and you can show that this sample variance is actually an unbiased estimator for sigma square, a standard deviation. Okay. So if you take the expectation of S square now, you can show that this is an unbiased estimator for sigma square. So you do this calculation. This is an exercise for you. Okay. So you can show that S square is an unbiased estimator for the population variance, irrespective of, again, the PDF. Now you can again, if you know that what is the population mean mu, then you can define slightly differently. In the earlier case, we didn't know what is the population mean. Okay, we wanted to calculate the variance. Now, if you know what is the population mean, then you can define this estimator of a variance in a slightly different way. Here it is 1 over n times xi minus mean square. Okay. This is a standard definition of your variance, right? When you calculate the standard deviation. So in this case, you can also show that S square the expectation value of the S square again becomes sigma square. So S square is again an unbiased estimator for again sigma square. In the similar case, you can also write, covariance. So Bxy again it's 1 over n minus 1 times sum over xi minus x average times yi minus y average if you have more than 2 variables. Okay. And you can do again this simple algebra to find this as n over n minus 1 times xy average minus x average times y average. Now you can show again here that this is an unbiased estimator for the covariance Bxy for the two random variables x and y. Okay, with unknown mean. In the same way, you can also define another estimator for the correlation coefficient rho. So R is the estimator for rho, so which is defined as variance estimator for the variance over Sx and Sy. Okay. Now, actually here there's slightly, though we saw that S square is unbiased estimator for sigma square. Pxy hat is unbiased estimator for Pxy, but here you can show that this R, which is the ratio of these two, it's not an unbiased estimator, but it is only asymptotically unbiased. That means if you calculate the the expectation value of R, that will find it is equal to rho minus this rho times 1 minus rho square over 2n. Okay. Now this term, if n is small, you will have some finite. But if n is very, very large, large sample limit, then in that case you can make this tends to 0, and then R converges to 4. Okay, that's right. It's asymptotically unbiased. Okay, but still, if you do not know the PDF and you want to know the correlation coefficient, still you can use this estimator because of its simplicity, even if with the finite sample size. Now, let's see what is the uncertainty or error or the mean. Okay. So suppose you have an estimator theta, okay, and to know what is the uncertainty in our estimation or estimated value or estimate, okay. So we can calculate the its variance, okay, and which is defined as theta hat square expectation minus theta hat expectation square. So this basically gives you the measure of the variance of theta hat about its mean value. Okay, suppose the idea is that what is meaning of this variance means if you perform similar experiments large number of times, each time with same sample size L, and then you calculate what is the distributions between whatever every time you estimate the theta hat from each sample size and you look at the distribution, the variance that you get is what you it's given by this expression, okay, which we sometimes call statistical error of theta hat. Now you can, for the variance of the sample mean x bar, okay, which you can write like v of x hat. So if you now again do all this in algebra, then you can calculate from here that this will give you 1 over n square sum over expectation of xi xa minus mu square. Okay. And then further, doing this, you will find that this variance it will be equal to sigma square over n. Okay. Now, if n becomes very large, this becomes very small. So, sigma square is basically the variance of the x itself. Okay. Okay, so that was the uncertainty on the estimator for the mean, estimate of the mean. Now, similarly, you can
Sir,
write.
Sir, like you calculated the variance of the estimator, but
Yeah,
is it always true that the mean of the estimator will coincide with my actual parameters value? I mean, there can be a shift also, right?
yeah, there will be shift. So the point is that since in larger limits, the mean of the estimate, the mean of the estimator coincides with the actual mean, right?
Yes, sir.
Because that's why we call it the unbiased estimator. So as similarly in the large N limit, automatically you can see from this that the error will be 0.
Okay, okay, sir.
Sigma square by n, right? So as it coincides with, as the mean coincides with the actual value, the error becomes 0. So if
So
the
the
small,
like
the error
that.
is large.
So like this, sir, error of the estimator will also go down. I mean, the spread will also go down, and the means will also coincide.
Exactly, yes.
Okay, sir.
Yeah, maybe pictorially it would have been better. One can show that, as you change, as you increase the sample size, you can see that the distribution goes smaller and smaller, and then the mean value also coincides, the estimate value also coincides with the true value. Okay. Now, similarly, you can show this error. You can also calculate the error on the variance. So again, the variance of the estimator S square, if you do the similar procedure, will end up with B of S square would be 1 over n times this, where mu is basically the kth, mu k is the kth central moment. So mu square is mu 2 square is basically sigma square, and mu 4 is fourth central moment. Okay. And using some simple generalization of the definition of S square, you can calculate mu k would be 1 over n minus 1 times I equal to 1 to n s xi minus x average to the power k. And similarly for the variance of the correlation coefficient R, or estimator for the correlation coefficient R, considering that you have 2D Gaussian PDF, can be written in terms of V of R, it's 1 over n times 1 minus rho square of square. So here you can note that though V xy hat x square and xy square are unbiased estimators for V of xy sigma sigma x square and sigma y square. This I already told earlier, that this correlation coefficient V of xy hat over xy is not unbiased estimator. Okay, for this this is only asymptotically unbiased. So one should be careful when applying this equation, but you can still, sometimes use it. Okay, so that's all for this one. Now I can, if you have any question, you ask me. Otherwise, I'll move on to maximum likelihood method. Checking this one. Open. Okay. Now we discussed about some estimators, okay, using their functional form. Now let's move on to this likelihood method. Now suppose in this case we don't know the functional form of the estimator, then we can use either say likelihood method, or we can also use the minimum least square method, okay, which will come later, okay, to estimate our parameter. Now what is likelihood function? Suppose we have a random variable x which has been measured n times, okay, and gives the observation x1 to xn, and x is described by some PDF f of x. Now the probability for x to be in x and x plus dx is written simply as f of x dx, right? Now if we assume that xi's are independent, so the probability for xi to be in xi and xi plus dxi for all I is again the same product of the f of xi times dxi, right? Or we can define this product of these probabilities as the likelihood function. Okay. Now, if f of x, like earlier case, depends on some parameter theta, then this likelihood function would basically depend on the theta. Okay. So this is basically product of f of xi theta. Now, think that this x, these xi's are independent, okay, and L is basically the joint probability of f of a given all observations, and it depends on the theta. Now you can say that this is L here is actually not a probability, okay, because xi's here are basically observations, but this is a function of theta, okay. So it's not same as the probability. So the L is the likelihood is a function of the parameter given some observations or given some data sample. Okay, so what is maximum likelihood method? It's basically a technique that to estimate the values of the parameter, given that you have some finite data sample. Okay, and the estimators, theta for the parameter theta hat for the parameter theta, which maximizes this likelihood function, is called the maximum likelihood estimate. Okay, so if we have a parameter theta and we consider some estimator theta hat that maximizes this likelihood, would be called maximum likelihood estimator. So how do we get that? What is theta hat? We simply maximize L with respect to the thetas. Okay. So, and then we solve for this equation and find what is the form of the theta. Okay. So if you may have sometimes, it can be possible that you can do it analytically if the functional form of L is well known, or you may have to do it, numerically, right? So if we have, say, more than one local maximum, then you can take the highest one. Okay, you can. And the estimators theta, this vector of theta means you may have more than one parameters. So usually will be written as vector of theta hat. Okay. Now, what is the advantage of this maximum likelihood method? Because it's simple, okay, and it is easy to use, and you don't need to do binning. So you can consider individual events instead of binning them into histograms. Now let's consider again the same example of
Sir, can you previous slide?
yeah.
So, sir, I could not understand this argument that this method does not need a meaning, because let's say if I have a root histogram where my some data is filled up, so and I have some function and I want to fit it, and I want to do it in this maximum likelihood manner. So obviously, if I increase my number of binnings, so I have more degrees of freedom, and my fitting will obviously depends. The fitting will depend on the number of binnings. So let's say if I have a chorus binning, I may have some different. I mean, the fit will be, let's say, good or worse depending on the number of binnings. So I could not follow why this.
Now,
I
so
mean,
what you are saying that you already have the histogram, right?
Yes, yes,
So
yes.
you have already filled the histogram, and then you are trying to do the fit. That is
Yes.
possible.
Yeah.
So
So
we
when
have
I
histogram. Yeah. So let me tell you. So if you already have a bin histogram and you want to do the fit, that is possible using maximum likelihood method. But what I am saying is that it is not necessary to make the binning.
okay.
So you can always use individual events, okay,
Mhm.
to do the fit, which is called on-bin likelihood fit. Okay.
So can you repeat what likelihood did you say?
On-bin likelihood fit. So you
Unbin.
don't bin it. Okay. So usually you don't bin you consider events individually. Okay. So consider the probabilities of the events individually. But if you bin it, then we'll come to that at the end of this slides. Okay. The bin likelihood fit. Okay. But without having that, you can still do the maximum likelihood.
Okay.
Okay. So you can simply consider the data sample without putting into the histogram. That's what I mean. So now consider again the same, example of radioactive decay. Okay. Now consider, suppose you have a sample of 50 measurements, which you can do this exercise just generating 50 events, assuming some parameter value. Okay. Say in this case, for this example, it is done the same way. I just took these plots from the book, but you can do yourself this exercise. Okay, just generate 50 or 100 measurements, assuming some, say in this case it is, no, sorry, this is not the exponential decay, this is simply the Gaussian. Okay, with two parameters, mu and mu equal 0.2 and sigma equal 0.1 is the true value that is used to generate 50 measurements. Now we assume that these 50 measurements are actually observations. Okay. Now we want to perform a likelihood for these parameters, mu and sigma, assuming that we don't know that what is the value is not known. Suppose somebody generated this sample and gave you as observations. You don't know what is the value of mu and sigma. You only know that these are Gaussian distributed. Okay, and you want to do the fit to get what is the value of the parameter. Okay, now what you can do is you can, for each events, you assume the the PDF, then you write the joint likelihood, joint PDF for 50 events, which is your likelihood, and then you maximize the likelihood. Okay, so if you do that, you will get, from this. Here you can see that the left side is yeah. Yeah, this is the example here. This plot here actually is showing what, that you can show that when the likelihood is maximized, it is showing for different values of the likelihood. Actually, it's not likelihood; it's showing log likelihood. I'll come to that why we need actually log likelihood instead of likelihood. So as you can see that for the true parameters, the log likelihood value is around 41. Okay, the maximum value of the likelihood. And if you calculate this likelihood for different values of the likelihood, you can show that when the log likelihood is very close to actually the true value, then you can show the ML4HEP, which maximizes the likelihood, gives you the log likelihood about 41.2, and you can show that it is pretty close to what is actually given by the true parameter. Okay, but when the log likelihood is smaller, for example, this right side plots, when the log likelihood is about 14, you can see that this deviates quite far from the actual two data points. And when it is around, say, 19, it is peaking around this point, but the shape is not exactly same. Okay. So the one which gives the maximum value is close to the true parameter. That's what the example gives. Now we can look at another example, the exponential decay, okay, exponential distribution. Now we consider that the exponential PDF with the mean value of the tau parameter, mean lifetime tau. Okay, so which will be 1 over tau with the minus t by tau. So this describes your proper decay times for radioactive decay. Suppose you have some measured value of the time for n decays, T1 to Tn. Now the task is to do the maximum likelihood fit, okay, and calculate the value of the parameter. Okay, tau. I don't know why did I write alpha, it should be tau. Okay, now you can define the likelihood for the tau is the product of the probabilities. Now, if you simply, since here the functional form it's known, you can actually do this maximization analytically, okay, in this case. So as we saw in the previous slide from the plots, that instead of the likelihood, it is actually convenient to maximize log likelihood, okay? Because likelihood, the likelihood function is a product of the probabilities. When you take the log likelihood, it will become sum of the log of the probabilities, right? And it will become a monotonically increasing function. So it's easy to do the maximization. Okay, and the parameter values which maximizes the likelihood will also maximize the log likelihood, and it is more convenient to use the log likelihood instead of the likelihood function. So if you do that, now we use the log likelihood function, which is again the sum of the log of the individual PDFs. Okay, now you can write it in more better form. And then if you maximize it with respect to the parameter tau, then you will get a functional form for the tau hat. Okay, now the tau hat, you know that it was the mean lifetime. Okay, now you can see that it coincides with what we had defined earlier for a mean value, mean estimator for the mean, right? In this case, the ML estimator gives the same as the defined estimator, generic estimator for the mean value. Okay, now here you can again calculate that, if you calculate the expectation value of the tau hat, which is again same as a sample mean for this PDF, okay, exponential PDF, it's basically same as what we did before. So you'll get the expectation value of tau hat is same as tau. So tau hat is an unbiased estimator for tau. Okay. So it was already discussed in the previous case. Okay. Now we can do same thing, but we can do some, instead of doing it analytically, let's do really a Monte Carlo simulation and do the fitting. Okay, now you can generate sample of 50 decay times, okay, using some exponential decay with some true parameter, true value of the true value of the lifetime parameter tau, and then you try to do the calculate the maximize the likelihood. Okay, and then compare this to the true value, and from that you can draw the function using the estimated value and the true value and see that you get the result correctly. So in this example that is in the book, for the 50 decay times, the estimated value is around 1.062 compared to the true value 1. Okay, and if you increase the statistics, then it would become closer and closer to the true value. Okay, so you can try this as an exercise. Some of this exercise will be done during the school, the main school. So I think by Professor Silpijan, she will be doing some of the exercise, some of the tutorials which will cover some of these exercises. Then let's take, again we come back to the function of this parameter. Suppose a is a function of this sum of this parameter theta. Now if we write, since we can write del L over del theta is del L over del A times del A over del theta, and since a is a function of theta, so del A by del theta is not 0. So then you can write that del L by del A equal to 0. So if theta maximizes L and A is a function of theta, that A will also maximize L. Okay, that's the point. Okay, so the ML estimator for A can be simply obtained by evaluating the function with respect to the original ML estimator for theta. So for ML estimator for A, it's simply as A of theta hat. Okay. So if you know the functional form and you want to know what is the estimate for A or estimate for that function, and if you know the estimate for the parameter, then you can calculate the estimate for that function. Okay. So since we knew that estimate for the estimator for tau, which is tau hat, now if we want to calculate the estimator for decay constant, which is inverse of the lifetime, okay, 1/tau hat, then we can simply write the estimator for lambda hat is 1/tau hat. Okay. So then if you try to calculate the expectation value of lambda hat, then you will see that this lambda hat doesn't actually converge to lambda. I mean, doesn't give you exactly to lambda. So you get 1/tau or lambda times n by n minus 1. That means only when n is very large, okay, then this will become 1, second part of this, and lambda will be lambda hat will converge to lambda. So that means this is only asymptotically unbiased. Now let's discuss about the Gaussian PDF. So we discussed the exponential PDF. Now we can discuss about the Gaussian PDF. So suppose we have say n measurements of random variable x, which are assumed to be distributed according to the Gaussian PDF with unknown mean and sigma. Now you can also for this PDF you can calculate the log likelihood function. Okay. So which will be like this. Now if you maximize this log likelihood, then you will get the ML estimator for mean and sigma. Again, the ML estimator for mean is simply the sample mean again, and if you repeat the same procedure, the ML estimate for sigma square will be sigma square hat will be 1/n times xi minus, here you can see that it is using the ML estimator for mean in the ML estimator for the sigma square.
Sir, I have one question in the last expression. Here it is written that sigma square hat is 1/n, but before some slides you have shown that sample variance is proportional to 1 by n minus 1.
Yes,
So
so that was the functional form of the sample variance. Okay,
here
estimate
sigma
for the
square
sample
hat is
variance.
what? It is not.
Yeah, so
Is
at the
it?
same time, if you remember, I said if you know the mean, then the sample variance capital S square was defined like 1/n times sum over xi minus mu square, right?
Yes.
Actually,
Yes.
I
Yes.
do not have in the same slide, but it is in the reference slide, so I have to close this. But so in this case, you can see that if we have an estimator for the mean, and since this estimator for the mean mu hat is an unbiased estimator, so this is used here, okay, in the estimator for the variance, and so the expression is not exactly same as the sample variance. Okay.
Okay. Okay. Yes.
Okay. Now here you can again show as an exercise that the expectation value of mu hat will be mean. That means this is should be a consistent unbiased estimators. Okay. But if you take the expectation value of sigma square hat, okay, so this will be again n minus 1 by n times sigma square. So since this factor is there, only when n is large, this will become sigma square. So this is only asymptotically unbiased. Okay. And again, what you were asking earlier, that the a square 1 over n minus 1. Okay, if you define that way, then it will be an unbiased estimator for the variance for any PDM. But the ML estimator for the variance, which we got from here, using the maximization of the likelihood, is not an unbiased estimator. Okay, but if you want an unbiased estimator, you can use the sample variance here. But if you want ML estimator for the variance, which is slightly different, in that case, it will not be an, it will be only asymptotically unbiased. Okay. But sample variance is not an ML estimator. You cannot, I mean, this is true for all PDFs, but it's not an ML estimator. Okay, now we discussed a few cases. Now let's discuss, given that, suppose we have some data sample, then we did the maximum likelihood fit, we got the estimate value. How do we code the error or uncertainty on that estimated value, or uncertainty on the estimate? Okay, so that means if we perform this experiment, repeatedly for large number of times, and every time we get the estimate from that data sample, it will have some variations, right? And what is the spread in that? That's what we want to know. Okay. So one way of estimating it by considering the variance or the standard deviation of the estimator. So there are different ways of estimating the variance of the estimator. So there are these 4 methods that will be discussed. So the analytic method, where if you can calculate analytically the expression for this variance, or we can use Monte Carlo method, generating Monte Carlo events, and then from these Monte Carlo events calculating the variance. Then there is simple raw form of facet bound, which gives you some expression to calculate the variance, or graphical method. Okay. Now let's first discuss about the analytic method. So in certain cases, you can actually be able to compute the variance using the analytic expression. So for example, when we have in this case exponential distribution with mean lifetime tau, which is estimated as a sample mean. In this case, you can calculate this variance by simply doing analytic. So from the definition of the variance, which is tau hat square expectation minus tau hat expectation square. So if you do this, rewrite it, and then expand it properly, then you can calculate. Again, this is small exercise for you to do this full calculation, and you should get that it should be tau square by n. If you just simply expand this integration, you will get it. Because, okay, you'll get tau square by n. So that means, again, this is, you remember earlier, right? We got sigma square by n, right? The variance for the mean. Now you can note that this variance is a function of the 2 parameter tau, which is not known. So how do we report the error? So here from this expression we got from this analytic method, we got tau square by n, but tau is not actually known. That's the true value. Okay. So how do we actually report it? And we know that the transformation invariance, that means the function of a variable. Okay, it's a function of a random number is itself a random number, right? So which we use, like if a depends on theta, then we can write the estimator for a, which is called transformation invariance. In that case, we can obtain this ML estimate for the variance sigma hat square, which is tau square by n, using, since tau hat square is a function of tau, we can simply replace tau by its own ML estimator tau hat. So when we report it, we can report simply as sigma hat square is tau hat square by. Okay. So if our result is reported as, when the estimate is reported as tau hat, so say 5.72, then plus minus something. So this plus minus something comes up from this sigma hat square. Okay. Okay. Now the second method, which is the Monte Carlo method. So in this case, what you can do is this method is useful if you cannot compute this analytically. So you can resort to the Monte Carlo techniques. So in this case, you can simply generate large number of experiments. So for each experiment, you have n observations, okay? And from each observations, from each set of observations, you estimate the ML estimate. You get the ML estimate using the standard method of maximum likelihood, and then you look at the distributions, okay? And from these distributions, you can get what is the sigma from this. Okay, that's the typical way we do the Monte Carlo method. So, but when you generate this, different and many experiments, in that case, what value will you use as a true parameter? Okay, we don't know the true parameter. We have only the ML estimates, right? Given an observation, we have only the ML estimate. Then, when you generate these pseudo experiments or Monte Carlo using the Monte Carlo program, then in that case, we can simply use the ML estimate as our true value of the parameter to generate these pseudo data sets. Okay, and from these pseudo data sets, we re-estimate the values of tau hat, and from that distributions, we get what is the sigma of our estimate. Okay, that's the idea. So this is actually an exercise can be done. You can do it.
Sir, like we have to do something to make sure that the Monte Carlo's distribution, looks alike the real experiment. I mean, there must be something.
Yeah.
Otherwise,
So yes. So what we are doing here, Monte Carlo. That is when you are doing, say, what you are talking is mostly it's applicable, I think, when you are doing data MC comparison, right? For the what do I mean? For the hypothesis test, you mean, right?
yes, sir.
So in this case, this is something different I am talking about. So here, suppose you have a data set, okay, and you want to
Yes.
estimate some parameter. So you have an observed data set, okay, and you want to estimate the parameter of your PDF, okay, when parameter of your for your PDF. Then in that case, what you will do? You will do maximum likelihood fit to that observed data set, right? And
Yes,
then
sir.
you will get some results of your estimator, results of your parameter. Okay, say in this case, say some theta. Okay, now you don't know what is the exact value of that parameter, so you only have an estimate. Now what you want to quote is that I estimated this value from my observed result, or from my set of observations or set of observed sample. Now I want to quote an error on this estimate. Okay, so how you quote that error? You can generate, since you have already estimated this, right? Estimated this from the fit, from the maximum likelihood fit, and now you can generate pseudo events, given that you know the PDF, right? and you know and you have an estimated value of the parameter. You use that estimated value of the parameter as your true parameter and generate pseudo observations. Okay, so you will get for each experiment you get again n number of observations. You calculate again the parameter theta. Okay, similarly keep doing, say, 1,000 times. Okay, every time you will be getting slightly different values and you will have a distribution. So that will basically give a spread over your theta hat, and that you can quote as the error, statistical error on your estimated value of the parameter. Okay.
So, sir, that is just like finding the variance of tau cap.
Exactly. Yeah. So you want to find the variance of tau hat if you don't know how to do it analytically.
So,
But
sir,
there are
why
also, of course,
do
other ways.
sir, do we need to do Monte Carlo? I mean, I got 1000 tau caps from different experiments, so I can just find the variance, right?
No. Different experiments. When you have 1,000, when you have sample, say like 1,000 events, okay, but that's one experiment. So from 1,000 observations, you are estimating one.
Okay.
Sir, if I understood correctly, you are trying to say, the fitting has to be performed 1,000 times, and it will give us 1,000 values, and if we plot that, the spread of that will give you the error
Yeah,
on.
but that 1,000 times you have only one data sample.
Yeah, exactly.
So you have only one data sample. So if you do same data samples 1,000 times, you will get always the same value.
Okay.
Okay, so you want to generate pseudo experiments 1,000 times using the estimated value from the data sample.
Correct.
Okay.
So, sir, this is, understood correctly. So, I just wanted to extend my question on this. So, when we, let's say we perform this maximum likelihood fit and we get the parameter value, and after doing this toy model kind of thing, repeating the experiments 1,000 times, we get the error as well.
Exactly.
So, let's say I want to quantify how best is my fit. So from, let's say, what we do in the root is we get the chi-square value or something like that. So that my question is, I want to know your comment on this, whether this chi-square will correctly define the correctness of fit, or something if I make a ratio of my fit function to the data and check whether it is equal to 1. How one should check the correctness of the fit.
So chi-square is you are doing it actually. This is one method of checking the goodness of it. What you are talking about to check the goodness of the fit, right? So the chi-square method is one of the method. There is also other methods to check the goodness of it. I will discuss one, but you can look at the literature to have. There are other methods also.
Sir, can you give some reference, or because actually I am dealing with such a problem, and I would like to know, because I tried by myself, and because I want to do the fitting, and I want to compare 2-3 methods, so that I am aware that what kind of fits are the best in this possible scenario when we are dealing with the maximum likelihood fits.
Yeah, so you can look at, there are 2-3 methods given in this reference book, which I showed in the beginning, no, Glenn Cowan.
Okay.
Yeah, so if you look at the chapter on maximum likelihood, so I will only mention one of them, which is the Monte Carlo method, but there are other methods given. One of them is the chi-square that you said. Okay.
Yes.
And the ratio of the likelihood.
Yeah.
Yeah.
Sir, let's say naively, if we make the fitting, and we may, let's say I make the ratio of my fit function to the data what I have, and check whether the ratio is coming around 1 or not. So let's say if I have my point, the ratio close to 1, I can say it will be a good fit, or if it's deviating more, it will be a bad fit. This is naively one can check. This is what I understood. In any case of fit we are performing. Yeah, is
Yeah.
it correct?
Yeah, that what you are saying is correct. I mean, the point is that when you calculate the ratio of the likelihood, okay, then from that you can actually it. Yeah, from that you can define maybe I can discuss a bit more about this in the tomorrow lecture.
Okay, sir. Maybe we can
Yeah.
discuss
So
it
from
later.
there, actually, you can get a chi-square kind of distribution. Okay, and from from that you can. I mean, the point is that if you take this ratio of the likelihood, okay, and
Yes.
if you take the distribution of the minus 2 times log likelihood, okay, so that is supposed to be like chi-square, okay, and to my understanding, if you look at the distribution of that, okay, and if from that distribution, I mean this will be distributed according to chi-square for, say, the number of degrees of freedom that you can calculate from there, and from that distribution you can say whether your fit is good or not, and you compare that to the observed chi-square that you have for your I think for your observed set of for your set of observations. Maybe I'll come back to that probably tomorrow. I can try to write it in more detailed way and then see. Okay.
Okay, sir. Okay.
Yeah. Are there any more questions? There's something else was being asked. No, who was asking that?
Yes, sir. It is. I got it, sir.
Yeah. Okay. Okay. Thanks. Okay. So now, yeah. So we can continue on that. Now let's say, so here this is the thing that we are talking about from the Monte Carlo method. So you have from the set of observations you got the sample mean, okay, which is tau hat mean, which is you got something like 1.05. Then you use that as your true value, okay, of the estimator, and then regenerate, say, sorry, I think what I yeah, so from this slide, yeah, the ML estimate that you got is, say, 1.062 from the 50 observations, and then you use this 1.062 to generate 1,000 further experiments, each having 50 measurements, okay, and from those 1,000 experiments, you estimate again the tau hat for each of them, and then look at the distributions. And this is the mean of that distribution, the mean of tau hats, which is very close to the tau hat itself. Okay, and then from here the standard deviation you can get from this distribution, which is given as 0.15 for this case. Okay, so here you can see that essentially this will be sigma hat will be tau hat over square root of n. If you calculate that, you take that 1 over the tau hat value, estimated value, times square root of 50, it gives you very similar to what you got from the this is analytic expression we got, right? It's tau hat over square root of n. And from the Monte Carlo method and from the analytic method, it comes out to be very much similar. Okay. Yeah. Okay. The third method is basically comes from an inequality. So this is called Rao-Cramer-Sachet inequality, which is also called the information inequality. This provides a lower bound on an estimator's variance. So suppose B is your bias, okay, for this estimator, then this inequality is basically defined as B of theta hat is greater than equal to 1 plus del B by del theta square over expectation value of del square log L by del theta square. Okay. So in case this is equal, the estimator is usually called the efficient. That means minimum variance. Okay. One can show that this ML estimator it's I mean, as we have already actually discussed this, that efficient in large sample limit. So in that case, in practice we can assume that the efficiency this is efficient and the bias is 0 in order to calculate the variance on the estimator. Okay, so in the practical purposes, we will assume that B equal to 0 and use this equation. Okay, so in that case, it will be simply V of theta equal to 1 over expectation value of L del square log L by del theta square. Now, if you now consider again this same exponential distribution and calculate the variance with respect to the variance of the tau, then you will get del square log L by del tau square. If you do this expansion, you will get n by tau square times this 1 minus 2 tau hat by tau. Okay. Now, from this, now you can write this V of tau hat would be 1 over this term that we calculated. And now if you redo this little bit of expansion, so you will get, approximately, it's actually not equal, but approximately tau square over n. Okay. Okay, so this is exactly, you can see that this is the same as the analytic calculation. Okay. And this equality actually in this case holds because tau hat was an efficient estimator of the tau. Now you can do the same if we have more than one parameter. So in that case, the corresponding formula will be the inverse of the covariance matrix Vij. Okay, so you can write the inverse of the Vij would be del square log L by del theta I times del theta j expectation. Okay, so if you do this calculation, we'll end up with n times this integration over the PDF f of x theta times the double derivative of this log of f of x theta. And then from here you can see that the covariance is also inversely proportional to the n. Okay, which is same, proportionality is similar to the sigma square itself. Okay, so that means as the result will improve or the statistical errors will decrease as we increase the n. Okay, now in many cases, this is not always practical to compute the RCF bound analytically. Okay, because you might be able to do this, particularly this the expectation value. So in that case, what is practically done, okay, and assuming that the data sample is large, okay, so this is, you can simply take from the measure data, the ML estimates, you can evaluate this double derivative at the value of the ML estimate. Okay, that means the inverse of the variance, okay, will be, or inverse of the covariance will be simply written as minus double derivative of log L with respect to d theta I at del theta I and del theta j at theta equal to theta hat. Okay, so you calculate the derivative and then take the value at the value of the estimate. Okay, and in case of the single parameter, it is the same, just that it's a one parameter, 1 over theta del theta square. Okay, so this is the usual method for estimating the covariance matrix when the likelihood function is maximized usually using numerical method. Okay, now the last one is basically an extension of this RCF bound. Okay. So which is called the graphical method, and this is I mean mostly used, if I understood correctly, and you can use it easily. So this is, if you simply expand this log likelihood function about the ML estimate theta hat, then what you will get is, if we expand log of L theta around theta hat, so you'll get log of L theta hat plus the first derivative term, okay, then the second derivative term. Okay, now the first derivative term is the one that maximizes L, right? So this should be 0. At L equal to L max, this term will be, first derivative term will be 0. So you will end up with only second derivative term. Okay, so you can write then that log of L theta, since theta hat maximizes the log likelihood, so log of L theta will be log of L max times minus this theta minus theta hat square by this factor is from the RCF bound is the sigma square, right? This del square log L by del theta square at theta equal to theta hat from the previous slide. So we can derive this as the second term as theta minus theta hat square, what, twice sigma theta hat square. Okay, now if you vary theta by theta hat plus minus sigma theta hat square, plus minus sigma theta hat, okay, then what will happen? The log of L max will be reduced by just half. Okay, so you change this theta by sigma theta, the log of L max will be reduced by half. So which you can see from this picture. So as you change the parameter, okay, theta, the log L value will change, right? And the value where the log L is maximum, which corresponds to L max, is gives you the estimate. Okay, now as you move away by sigma theta, the log L value will reduce by half. So what you can do is, once you estimate the parameter value from L max, then you vary this log L. Okay, so you vary this log L, or you vary this, you can do otherwise twice of log L. In that case, it will be plus minus 1. So you take twice of log L. CMS students, I mean, must have seen this scanning of the minus 2 log L, right? Plots, which will look like a parabola in that case. So here also it is showing opposite. What you usually see is the one where the minus of 2 log L is minimum. Okay, since log L is maximum at theta hat, so minus 2 log L will be minimum at the value of the parameter, and then if you take if you vary that parameter, it will change, and where it changes by plus minus, it changes by half in case of this one, or if you take minus 2 times log L, it will change by 1. So there it will be the 1 sigma error. Okay, so here in this case, you can see that this values will give you the 1 sigma error for this estimate. Okay, and you can also see that in this case it is reasonably close to the parabola. Okay. And this is because this parabolic picture comes because the likelihood function usually in the large sample limit becomes Gaussian type. Okay, that's why you expect this to be about to have parabolic picture. Okay. Is there any questions on this regarding how do we estimate the errors on the estimates? No. Okay. I think what we can do is we can stop here because I have quite a few slides more and then continue from here tomorrow. Okay, and then also I can add to this the chi-square one. If you have some questions, then we can discuss. Otherwise, we can stop from here.
Sir, in maximum likelihood, like we have to, I mean, we are kind of guessing the distribution.
Yeah, you are kind of assuming the distribution.
If my, under certain conditions, two distributions with different parameters can look alike. So that would create some problems, right?
No, I didn't get this.
Sir, I mean, two different functions with different parameters can sometimes look alike, right?
That is possible.
So
But-
then, what I want to say is like we can guess the function wrong.
Yeah, so then that comes to kind of which hypothesis is correct. Then that would come to a hypothesis test. That given the data sample, first you want to know which hypothesis is correct, right? And now given the hypothesis, you want to estimate the parameter.
Okay, sir.
So first, like once if we don't know like if we don't know whether the X is exist or not, we cannot determine its mass, right? So
Yes, sir.
first, when we see some distributions, we want to know, okay, whether my hypothesis is correct. Like if there is a bomb, if that is, if there is not a really bomb, it's just a fluctuation or something, then if we just use some say like a derive function, we may not get the correct result, right?
Yes, sir.
So the point is that we have to first say that okay, there is actually on some smooth distribution there is a bump with some Bright-Wigner function, Bright-Wigner kind of peak, and then we use the Bright-Wigner function, okay, then to get what is the value of my mass, for example, and the width of that bump. So the point is that when you want to do, you have to assume some hypothesis or some kind of function for a given distribution, and then you find the parameter. And if the assumption is wrong, then of course your parameter will not be correct.
Okay, sir.
And the parameter depends on what hypothesis you are assuming and what PDF you are assuming. And from the fit, of course, you can also know whether the fit is good or not, right? That comes to goodness of it. That if the function is not correct, that means the fit would not be good.
That can also serve as a test. Yeah.
Yeah, that also gives you as a test.
Okay, sir.